if an object is neither still nor moving at constant speed, right, which are the two situations covered by Newton's first law, how is it moving then? If it's not at rest and it's not at constant speed, what is it doing? If you think about that for a minute, I think you might come up with some of the answers. So let's proceed and talk about that part, because then we'll have covered all the parts of possible motion. Okay, so it turns out there's actually three possibilities if you're not at rest and you're not moving at constant speed. There is speeding up, right? Slowing down, or, and this is the one that tends to be tricky for students, changing direction. Okay, so you're either at rest, or you're moving at constant speed, or you're speeding up, slowing down, changing direction. There's really no other kind of motion that's possible. Okay, now luckily for us, Newton's first law, as the name suggests, was not his only law. He actually has a couple others up his sleeve, and it's the next law, Newton's second law, that's going to be the one that tells us about what are the forces doing when we have one of these types of motions here, when we have speeding up, slowing down, or changing direction. By the way, what's another name for speeding up or slowing down? You got it, acceleration, right? Now, believe it or not, and again, this is the tricky part for students, changing direction also qualifies as acceleration. So we will talk more about that later in the school year, but for now, acceleration can be speeding up, slowing down, which you obviously knew about, or changing direction, okay? And so now we get to Newton's second law, and Newton's second law is interesting in the sense that if I were to type it out in words, you would groan. It's kind of gross to look at in words, okay? But the cool thing about Newton's second law is that there's a really easy way to write it, okay? There's a really easy way to write it. F equals ma, okay? And what that tells us is that the force on an object is equal to the mass of the object times the acceleration that experiences. Now, we're going to use this formula later on in the year. I'm not really too concerned about you using the formula now, but it does show us something that's really important, a relationship between force and acceleration, okay? Now, I'm going to write this a little bit differently over here, okay, to emphasize something that's really important. Okay, so we're going to write here, oopsie, got some pen issues, F net, okay, as a subscript, F net equals ma. Okay, so and all net is just another word, although you need to learn it, okay? Net is just a word for unbalanced, okay? And what that says is this. It says, Newton's second law says the following: if you have an unbalanced force, you are going to have acceleration, okay? Right? Now on a free body diagram, okay, we'll finish with a free body diagram. Oopsie. Okay, so in a free body diagram, it would tell us if we knew that an object wasn't accelerating, like it was speeding up, slowing down, or changing direction, we would know that some of the arrow lengths on the free body diagram would be a different length. So let's finish with doing a free body diagram of this block again, but this time we're going to assume that it's accelerating to the right. Okay, so we'll say that it's speeding up to the right. In fact, let's type that. Oops. Speeding up to the right. Okay, and all that means, okay, the only thing that's going to change in this diagram here is, and I'm going to pause the video and just go ahead and draw it out, and then I'll talk it out. That way we won't waste too much more time. Okay, you've seen that I've reproduced the free body diagram from the block, but now we're going to assume that Pam and Chris are pushing and pulling to the right hard enough so that it actually causes the block to accelerate, to speed up to the right. And so the only difference in the free body diagram is you'll see now that the arrow lengths, right, the forces of Chris and Pam, or the rope, because Pam's pulling on the rope, that those lengths are a longer length than the friction is backward. So you see that in the horizontal direction, right, there's an unbalanced force, okay? There's more to the right than to the left. And Newton's second law, right, F equals ma, tells us that an unbalanced force will produce an acceleration in that direction. So when you draw free body diagrams, you have to know a little bit about the motion, because the motion will then tell you about whether the forces are balanced or not. And that'll give you an idea about how long to draw your arrows. It doesn't really change what arrows you draw, but it changes how long the arrows are. And that's a crucial thing to pay attention to. Okay, I hope you got a lot out of this first lesson. We're gonna, when I see you in class next time, we're going to turn around and apply this to some real world problems.